is I have 2.5 hours worth of slides, and I don't think they gave me that much time. So I'll do this sort of like I do in class very quickly. A quick overview of what the difference is between, for instance, security, when we're talking IT versus OT. Just so everybody remembers, OT is this world where safe operation of your system, regardless of what happens, whatever the environment changes, attackers, I don't care what goes wrong, what breaks. If your refinery is no longer operating in a safe mode, it's generally a bad day. And so therefore, unlike IT systems where if you break an IT system, nobody's killed by missing an email, people do get killed if you mess up your OT systems. So the whole idea of security, what we're trying to assure is safe continued operation, which leads right to the word resiliency. Because resilience is your ability to anticipate, withstand, recover from, and or evolve to improve your capabilities in face of adverse conditions, stress, attacks on the supporting on the whole system. In this case, we're looking at the cyber side, so we're going to apply these same definitions to say, hey, can I still do what I'm supposed to do in spite of anything you do to my cyber resources? So the cyber resources that we're worried about or that we're going to be considering are your OT systems that provide your control systems, the communications to and from devices, the actual running of a little program inside a PLC. That is actually part of what we would call a cyber resource for your pipeline, your refinery, whatever to function. And so when we look at the world of IT security, everybody cares about three words: confidentiality, integrity, availability. When we look at OT, we're really looking at, can my system anticipate what's going to happen to it? Can it withstand whatever happens to it? And can it recover? This last one, and or evolve to improve capabilities, I think that was written in there by people that think that one of these days AIs will make it even better. But the evolving part right now, really, as we'll see as we go along, mainly involves a human operator going like, oh, this is happening, I need to do this. So whereas before I worried about the three words of CIA, here I'm more interested in anticipating, withstanding, and recovering aspects. When I look at how I do these things, and this is kind of an important concept here, that I have some sort of policies which are business desires. I try to explain to my students and everybody I talk to, policy is not a bad word. It's not 4 letters. It's longer than that. And what it really is just business desires. It's what do you want to do? I want to block this person from coming through a firewall. Well, you express that in terms of a policy. And then somebody comes along and goes to the compute layer, which is where I have all my stuff, and says, let me put a rule into this box which prohibits this from happening. So I have 2 different layers that I can play with. The policy layer, which is what I desire, and then the compute layer, which is where I actually have equipment and things I can program to do something. And then that all goes to this physical layer that actually has things happen. And my favorite example on that is, you can have a desire for your traffic lights to never have green on opposing sides. The all green traffic light problem. Well, let's turn them all green and see how the drivers sort it out. Well, there's actually a compute layer. So I have a policy that says we're not going to have all green. Well, I have a compute layer that runs a program that says the left turn is going from here, so these have to be red. When this left turn turns red, then this can turn green. So there's a program that manages all that in the compute layer that's supposedly meeting this policy. And that program running turns on and off lights on those poles, and that's your physical layer. That worked great for many, many years. And we use relays to do it. And then it's kind of funny because relays are subject to dirt and bugs. And actually, you can argue that's where the original term bug came from. Relays can fail. And so if a relay fails in one of these systems, the compute layer says, turn this light red, but if the relay doesn't respond in the physical thing, the light doesn't turn red. And so what happens? The lights end up the wrong color, and you have a problem. And so people came along and figured out they needed this control layer in the middle, and they didn't call it resilience, they called it something else. It was like a safety system where it made certain no matter what your compute layer thought you were doing, the only allowed states in the physical layer met certain cutouts in essence. And so therefore, you had a physical post-compute check to make certain that your traffic light pattern was going to be displayed as soon as the lights changed was legal among all the lights together. And you can buy little boxes today that they put into the traffic light systems that actually enforce that and make that happen. Using that same idea, we can, in essence, start looking at my compute layer tells my refinery, my pipeline, my whatever my OT system is, this is what I want to be doing. I can then insert, based on that knowledge, another layer that says, is this in line with where I want? In other words, opening this valve, turning on this pump. If I'm already in an overpressurization situation, I can't do that. And so the idea of putting a resilience layer in is just like the traffic control layer. And we already have it to a degree. We call it the safety instrumented system. But I want to be really clear here. The safety system, when you engage it, you are no longer in control. It is. And so the idea behind resilience is never to have to engage safety. To keep my pipeline in a pressure zone that's legal, to keep my refinery temperatures in a place that's still working. So I want to have some layer that in essence checks the compute layer against the physical conditions to say, am I where I want to be? Is this called a logic check, but it makes certain that other things don't get in the way and cause abnormal conditions. And so when I look at this as an emergent property and look at what I already have in place to do things, I have a lot of these things in place. For instance, if you are at all familiar with engineering of large complex systems, we have this thing called failure mode effects analysis, which is simply an engineering study of how does a system operate under various failure situations. If you get to this condition, what happens? If this fails, what do you do? And airplanes used to fall out of the sky all the time in the 1930s because something go wrong, it broke, and no longer could remain airborne. And this caused problems. Today, we don't see airplane crashes. Very, very rarely. I grew up as a child of the 60s and 70s, and there were regular airplane crashes on the news. Mostly due to weather, sometimes due to pilots, sometimes due to equipment. Today, airplane crashes are like that once in every couple year thing when somebody does something stupid like fly over a war zone and somebody shoots you down. And what's the difference? Well, the difference is we literally, as an industry, okay, engineers, pilots, everybody, FMEA'd failures out of airlines. They don't crash. They're safe. Today's refineries work way better than they did 30 years ago. Why? Because I've FMEA'd out all the things that go wrong, all the things that lead to things that go wrong, etc. Now, that worked great until we decided to connect everything to the internet, because the internet brings along this new thing called threats and these problems to our control systems that they always pretty much assume the control system is going to work the way it's supposed to work because that's what they relied upon, or that a sensor would stop sensing. Today, we have to look at this from a slightly different thing and say, hey, where can these disruptions come from? And the last piece that I have engineered in here, which is kind of an important aspect, if you go look at the Purdue model and the idea of isolating things into zones, the whole idea behind the Purdue model was to have things like your safety instrument system in its own safe, protected place. Nothing was going to affect it. You have other things into very isolated boxes. As I explained to students, if you run a pipeline across the middle of the United States, like we've argued several times recently, should we not, whatever. You have to have something that stops lightning from striking in Nebraska and hitting one of your control systems, and having that electricity uninterrupted. All the ones and zeros that leave that equipment when that happens, you really don't want those going everywhere from Canada to Louisiana or Texas, because you're going to have isolated problems along the way. And so you have to have some way of isolating those problems to their own little local neighborhood so they don't spread everywhere. And the Purdue model is specifically built for that. And so that's one of the things that we have that we can use for it. So going forward, we looked at this project and how we're going to put all these things together. And there were a few things that we didn't anticipate up front and didn't pay close attention to. And one of these is this, oh, wait, determining what proper is for any given thing is no longer non-trivial. It is very process specific. Excuse me. Pipelines have very specific overpressurization issues. You really don't want to have more pressure in a certain amount. But yet, if you don't have enough pressure, you don't get product movement at the rate you want. And it's not just pressurization at one point. You have 2,000 miles of pipeline. You have to worry your product leaving one end is being pushed because it has to flow to the other end. But if in the middle you have more pressure because that system is set a little higher, then stuff trying to get to the middle can't get there because you're trying to pump uphill. And so there's a lot of coordination. There's a lot of process specific, whether I'm in a particular refinery operation, a particular specific operation refinery. Refineries aren't one thing, by the way. Refineries are like a whole bunch of different chemical processes and separate vats, containers, systems, all working independently and some together, all to produce a stream of different products out of some common source material. A lot more complex than one thing comes in, one thing goes out. And so understanding what is the resilient mode of any one of these processes and which operations can be resilient and which ones aren't and what the issues are for each, it's not a generalizable answer. So that's led us to one set of problems. There'll be some others coming along, but I think we're making progress on how to deal with these. One of the answers that came out early on was, why can't we just pick something that improves, pick any one of those things, withstand? Let's just go make something that solves all my withstand problems, just like I have a confidentiality problem, an integrity problem, availability problems. Well, when you really look at a system in the IT world and you try to apply point security solutions, they never work because your problem walks around your point solution. And so the overall security of a complete system is an emergent property that's not defined by single elements, but is the result of multiple system interactions working together. So it's not just blocking a port, it's blocking a port plus encryption, plus access controls, plus this, plus that, all together make it so that my system becomes secure. Resiliency is going to be the same way. Just putting in that one layer and saying, hey, I slice in this one PC board and everything's good, not going to happen. Things will go around that. So you have to build an overlapping series of, call them defenses, that take care of each other and provide support. And to do that, you're still going to have to go back and look at what specific elements do I need in my system as a result of my desire for resilience. What do I have to measure? What do I have to be able to control? And it may not be directly things like, for instance, let's take a look at temperature in a particular process. Sure, I may have a heating element that provides heat to that process, but there are also flow elements through the process that matter. There are recirculation elements that matter. And so I have to look and figure out for each one, which ones are the drivers of the activities that I want to be able to control. And so when I start looking at it from that perspective, I can see I already have operational controls that I use for controlling security, for controlling the system running the way I want it to run. I use controls everywhere. Which ones of these do I have to label and understand to monitor and look at to make certain I'm resilient? Because it's one thing to say, my temperature's in the right place. It's another thing to say, and I've got a bubble that my temperature has to be plus or minus so many degrees under certain pressures. And so in a 3D graph, that forms this bubble. And I'm measuring pressure versus temperature versus flow rates. And as that individual point where I am right now moves around inside that bubble, as long as it's in the middle of the bubble, everybody's happy. Well, it's never going to be sitting in the middle of the bubble. It's going to move around in there. And as long as it's not moving dramatically towards one of the edges, I'm probably happy. But if it starts moving towards one of the edges, understanding what I need to do before it gets to that edge is the type of issue we're talking with resiliency. And so what I'm looking at, and what we originally start off with, was we have a list of top 20 security controls that actually take care of everything I do in security. Why can't I come up with a top 20 set of resiliency controls that I can sit there and manipulate? And this initial thinking got us a little ways down the road, but as we got into real details and started talking with an industry partner or two on some of the details on this, it turned out that, well, that pesky thing called details matter. And the fact is that since each process is a little different, it's not as simple as this. Which, to my chagrin, I have to say, I have to give Kenny Mesker from Chevron some credit on this and some others. We're talking when they kind of bring up the fact that, security is no different either. If you think you can do your 20 security controls in isolation of what you're trying to secure, that's why it doesn't work. And so when you look at this, I went back and said, okay, so what makes the 20 security controls work? A key concept, they're built from analyzing offense. What is someone going to do to me that upsets it? And so if I want to look at the 20 controls, if I want to develop a top X number of controls, it may not be 20, that's going to work on resilience, what causes non-resilience? What's going to upset my process? What's the offense that I'm playing against? And so when I looked at the top 20 controls that I use for security in OT, and they're numbered differently than they are numbered in the IT world because, for instance, things that are more likely to hurt you in OT, like secure network engineering, which, by the way, dropped off the 20 controls in IT recently, are higher. So the order's renumbered. The order's not that important. It's just these are slightly tailored to, these are things that, from a security perspective, in OT matter. And so I said, okay, let's look at what's offense. I need to be able to withstand. I need to be able to anticipate, recover. Evolve would be nice. But I have to apply these controls. And what is offense? My offense is you're going to lose view of your process. You can no longer see what's going on. You can no longer control what's going on. Or another agent can deny you the ability to view, deny you the control, or even deny you safety. And probably the most insidious of all, they can manipulate your view. You think you're viewing, it all looks right, the numbers all line up right, processes are reacting right, it's just not what's really happening. The same with your control and the same with safety. So if I look at those and apply this idea to the list, then suddenly I start looking and saying, which one of these controls make it so I can withstand something? Which one of these controls make it so I can anticipate something? Now, anticipate and withstand are kind of an interesting, I don't want to get into a semantic argument on the red and green coloring here, because a lot of the things that I will use to withstand do so because they anticipate an issue. The idea of securing having a secure network configuration all the way around with proper enclaves through zones and conduits, is that because I anticipate a problem, or is it because I want to withstand the problem? And the answer is both. But there was no really way to color these letters back and forth. You know, I thought about coloring every other letter, but that was going to take too long on the slide. But the bottom line, when we start looking at these, now I have a whole different direction on how we're going to start looking at our problem and what are we, you know, how do we move forward from this? Which is, how do I align it with these the concepts of I have to anticipate what's going to go wrong, I have to be able to withstand what's taking me out of my controlled position, etc. And this brings us to challenge number 2. As I mentioned earlier, there's some things we've uncovered along the way and why we're having problems just rapidly wrapping this thing up and coming up with an answer, because it's not so simple, is we're not there because bottom line in the middle here, it says each process has its own modes and its own path. And so we have to figure out how we're going to manage this aspect. The security controls still count and are still important because they really do defend the information side of the control processing of this. So I still have to have my control functions working. I still care about what we'll call even classic security of my control system networks and the equipment hanging on it. But in spite of that, or in lieu of that, if I have a process that's doing something, I have a couple different conditions I have to care about and understanding. For instance, that idea of ever-increasing temperature. Well, when to recognize it? Well, I can't make a simple rule that if 3 temperature readings in a row keep getting higher, it's a bad thing, because it might be moving to a good point. So when do I recognize something? When do I control it? When does it become a problem? That's an interesting aspect. Likewise, steady state. So, hey, your graph looks perfect. You're stuck right there in the middle where you want to be. Nothing's moving. Okay, that's in reality in most real systems not true. Things are changing. Things are moving. And so what am I missing? What am I not measuring? What is going wrong that I'm not seeing? Because if you look at any real process, they don't form nearly as nice a straight line as we would like them to. And so when I look at the resilience side, when I look at normal control processes, I have a set point. I want to get the pressure to 14. And so as it comes up, it goes a little above 14, goes a little below 14, comes a little above, a little below, and it wiggles into a position where it's pretty close to 14. Anybody that's had the engineering PID control loop class, you've done this on MATLAB numerous times, you understand how it works. Then you have to realize you really have to add in an error channel that adds noise, and then you have to add another channel in that brings in an outside influence that just moves it every so often, just because. And now see if you can get it to stay where you want it to stay, and what sort of compensations and how your system, and our control loops are built and designed to handle these things we're talking about. But what happens when that noise, when those changes aren't on the real physical process, but are only on the control process because somebody else is injecting either noise and or false data? And so at a certain point I have to figure out, in spite of all that, how do I know where am I now, where am I going? Because the safety system, if properly engineered, has its own set of sensors and controls that are going to say, you know what, you got here, we're at extremis now, I take over. And you don't want that you don't want to ever be to that point. So the question is, at what point and how do we determine that, and how do we make those measures against our systems? And when I look at how almost everything I have in most systems today are lined out, they're built solely to hit that word withstand. We're used to, in a physical process, something going wrong. A valve not closing correctly, a gauge not reading correctly, a thunderstorm coming through and dramatically changing the air temperature that's throughout your entire refinery. You're sitting on the coast of Texas, and it's 96 degrees in the afternoon, and we get a heavy thunderstorm comes through. The temperature will drop from 96 to 76 in a matter of minutes. That has a huge effect on these large chemical processes that are being heated and running things. When your air temps change, your exterior temperature of all your pipes and your containers change, this has a huge effect, and they see it. And they're used to that. Matter of fact, they watch the weather because when they know it's coming, what do? They, you know, change their process ever so slightly so they're ready for the change in air temperature, etc. But now I want to look at what I'm going to call the ICS attack phenomena, which is not only do you have to worry about that, which is a physical process issue that's facing you, I have to worry about malware getting on my system, and that's something I worry about the IT people taking care of for me, or the OT security people taking care of, so I don't have my malware a problem. But what happens when I lose visibility and control? And what happens when I lose my system? It's no longer really mine. I think I have visibility and control, but I really don't. It's not my system I'm looking at. And I'm going to say that when it comes down to number one, most of what we see right now in this space is really aimed at attacking that problem. How do I keep attackers out of my control networks? How do I make certain that they can't, change things, or if they change things, I know it? But I want to turn around and look at this, and where we really need to spend the time and effort now looking is understanding, how do I keep track of 2 and 3? Because 2 and 3 is where Stuxnet did all its damage in the uranium processing. It wasn't the fact that the malware got on their system. Malware gets on your system every day. Matter of fact, if you open up a really well network engineered system that has no real way for stuff to get in, you'll still find Conficker on it. Because Conficker is like mosquitoes in Texas after a lot of rain. They get in everywhere. You can't get rid of it. It just doesn't die. And so I've seen it on numerous systems when I go in and look. And, it's kind of one of those things, you're ready to see it. It's going to be there. It doesn't hurt anything because it doesn't have any avenue by which it can breed, which it can attack or do anything, but it's still there. So this malware problem, it's everywhere. The real problem is, what happens when things go wrong? What happens with something that's causing me not to understand my visibility or my control aspects? What happens when someone writes malware, like has been done and will be done again in the future, that causes you to lose the visibility and control? When we go back and we look at the Ukrainian situation, I look at the Ukrainian situation and I view it much like what we saw presented to us, and I've seen presented numerous other times. It's not that exciting of a OT type attack, because there was no question to the guys in the control room when they're sitting there staring at their monitor and their mouse is moving and they're not moving it. And, hey, let's take a video of this to show the boss, because I'm not doing this and it's doing this. What's going on here? That's, sure, it's a devastating attack. I lost control of my system, but I knew I lost control of my system. I knew that somebody else had control of my system. So what they do? They unplugged it. They managed to recover. Imagine the same thing if you thought you're controlling your system, but you're not. And so where we need to look at from resilience and the real strength of some of this stuff is these problem number 2 and problem number 3. Can you actually recognize and understand when your actions are making the control changes, they just may not be enough or proper, or when someone else is doing it for you? Because again, back to Stuxnet. What Stuxnet did that was so beautiful is it destroyed the stockpile of uranium and the centrifuges by just slowly tweaking little things over time in such a way that you got bad product, but it told you had good product. And it caused maintenance problems when it made it look like you just had bad maintenance, when in reality, no, it was specifically trying to break them, but it didn't do it in such a way that you ever noticed. So when I look at the bigger picture and what we need to be protecting and looking at from a resilience thing, It's much more so than just grabbing a hold and saying, oh, throw up this control. If this control turns to 14, we need to change it to 13 and everything will be good. So as we talk about this and have looked at this and analyzed it, and we look at what is an attack, what will it do to me? We picked one, for instance, like change a process control logic. How will your controls see the change? How will we, an operator set, recognize this change? Today's controls do see some of the changes and will see some of the deviations. Not necessarily noticeable by the operator, but what's really happening is, do today's controls actually see and understand the process change itself? That you thought you were building A, and now your process has changed, slightly tweaked, it's building B. And where this gets to be really, really interesting is when you look at a refinery, today a modern refinery can produce, we'll just say, a half dozen different outputs from the current set of oil coming in. And there's a recipe they've decided based on the quality of the oil and the market price of the output stuff that they could make, how they're going to do the mix, so they can get so much ethanol, so much of this, so much alkyd, so much. It's a wide variety of things that they can produce at any given time based on quality of input and their desire based on a market price. Well, what if someone changes that recipe? Your refinery is no longer going to work at the same performance that you thought you were working at. It's still going to produce output. How do you go back and see, as it's going along, that you are no longer doing you're not driving the ship anymore, someone else is. And I kind of make this like when we have self-driving cars, the hardest part for us to move from where we're driving a car to where we hop in a car and it takes us magically to our destination and we don't care like an airplane does, the hardest part is going to be that transition, which is you're sitting in the driver's seat, but they don't give you a steering wheel, but you can still see. You know, when we're in an airplane, if you think about it, it's not much different than a car. You get in, you buckle your 1966 seatbelt, and if you ever wonder what they did with all the seatbelts from the 60s, you now know where they are. Boeing bought them all. So did Airbus. And you sit down, you mind your business, and then they tell you it's time to get up because you're at your destination. But yet, we don't do that in a car. Okay, we don't even do that in an Uber if you think about it, because you're always watching out the front to see how your Uber driver's driving. I don't know many people that get to sit and watch how the pilot's flying to see if they like it. So the question is, who's in control? How do we know we're in control? And right now, we tend to think of all our major refineries, all these things that we're doing with all these control systems, that we're like the pilot in the front of the aircraft, that we see all these gauges and we're actually driving, when the complexity and other aspects of it, especially with all the things we can now do with, for instance, change your PLC program without you even knowing it, are you really driving that ship anymore, or are you now just sitting in the back like the passenger? And so one of the questions we're looking at right now, talking to Chevron and some other people, is we do have insight into what's happening on our network. Network security monitoring tells us all the things that are happening. And so we're looking at classifying them into, okay, this is normal behavior, this is an allowed thing, oh, this is rare. You know, if you're running a refinery and everything's running and doing the things you want, you're going to see valves open, valves close, temperatures go up, temperatures go down, flow rates change. All these things are normal. Seeing a PLC go into maintenance mode to update the program, that's not normal. And so the question is, how do we plot those and say, hey, here's a control that says, this is not normal operational behavior. You're going to have a resilience problem because you're changing something. And that's kind of where we're, I don't want to say stuck, but that's how far we've gotten. That's where we're chasing things right now. So at this point, I want to open it up to questions. everybody's still on mute or no one has questions?
Are we off mute?
Illinois is off mute. We can hear you, Art. Folks, if online, if you want to ask a question, remember unmute yourself.
Can I ask a question?
You can. Art the Bignev has a question.
Need to go here.
Yeah, that little round black thing up there.
Microphone?
The J bar.
On the back of the podium.
Oh, this one, right?
Yeah.
Okay. So thank you for the presentation, Art. And I have a question, related to the last slide when you talk about that the systems can see some, changes in the process and all of this. Can you give some insight about, let's say I see the change, right? Is there any chance in this kind of system which you are handling to reverse the actions which were taken by some, let's say, malicious actor in the system? Is there a chance to do this at all, or you have to have some sort of, because you send the command, something happened, the pressure change, right? By reducing the pressure, maybe you may have some local impact, but the thing's already propagated, right? So is there any kind of, I'm not clear about this kind of physical system, so maybe you can give some insight. Do we have a chance to really reverse the thing, or we have to simply compensate in some other way for changes which have been made, and what are the time constants for reaction? If you could give some insight into that.
Okay. To rephrase your question a little bit, what I heard you ask was specifically about if, let's say we have a valve and the valve suddenly starts to close, and I didn't ask the valve to close, and the PLC program probably didn't ask the valve to close, but somehow somebody threw up one of those nice little commands and told the valve to close, got to the PLC looked at it, says, okay, close the valve, and it's closed. I have to recognize that as that I didn't issue the command, the PLC didn't issue the command, the valve should not be closing, that the command came from somewhere else. Network security monitoring can give us some insight to individual commands coming from elsewhere. They should not have gotten there because of network engineering and other things, but assuming somehow it gets in there, because thinking you'll always keep bad guys out of your network is just wrong. So how fast can I make that change? I have to, one, recognize that, okay, this is a change that was not a desired change that we need to undo. And I think normal process controls will take care of this for me, for the simple reason that as the process goes along, various valves will be open and closed for various reasons. The operator does not operate all the things that happen. A lot of this is done by a program and PLCs and everything based on other conditions. The operator oversees. He's not actively making all these changes. Much like a plane flies in autopilot the vast majority of the time. So as this is all happening, if something gets slightly out of whack, like you're on autopilot, but you get a wind change and it moves you off your path and you now have to make an adjustment, operators can make those adjustments. Those sorts of attacks are not the type of thing that I'm really that worried about, because they're going to happen. They could happen because of physical breaking, just signals somewhere along the way get confused. A variety of things can go wrong on this whole chain of events, and you don't get quite the action you wanted, and you can make another action later and self-correct it. The bigger issue is one where I think I'm controlling something, and I'm not. Now, in the Ukraine issue, it became very obvious because they locked the engineers out of their own console, or they basically made their own console, so no matter what you did, you got to watch the mouse move and everything's going without you doing it. What would have been much more insidious had it been done this way had been the Ukraine operator's console still responding to the Ukraine operator and still looking like he thought it would look, when in reality, the attacker had their own version of the console that showed reality, and they were closing things and doing things And so someone would call up and say, hey, this bus just closed or just opened. Why? And the console operator looks and says, no, it's fine. I'm looking at it right here on my machine. See? It's fine. Those are the type of where we get into serious problems when you no longer have the connection between your control system, your operator, and the physical process, that disconnection. And so that's what we're looking for to see when would we see things that would lead to that type of event. Does that make sense?
Yeah, okay, thank you.
Art, this is Al. Maybe this is kind of building a little bit on the previous question, and you mentioned that the operator is not doing step-by-step valve controls, for example, or step-by-step detail control of the process, but rather they're initiating some program that is that seeks to, in the case of a refinery, take product of a certain chemical breakdown and produce products of a particular set of output products. What checks that program step by step? Because it should be, it's not so much to say, well, at this point, a valve should open, or at this point, I should increase the heater or heating element or whatever it is. But is there anything other than the device itself reporting back to the program that says that, yeah, the valve opened, just kind of like an acknowledgement that there's a command to open the valve, and then the valve responds, okay, I open to 3/4 or whatever was requested. What do you think in terms of step-by-step checking against the program that these actions actually took place, and then reporting deviations from that by some channel other than the device itself, which might not be trustworthy?
That's something that I've actually talked to people about. How do I know that what's actually happening is happening? And part of that has to be based on pure faith, based on, flow rates, things like that. I close a valve to stop the flow, my flow rate doesn't change. So one of these two is broken. Either the valve didn't close or the flow rate is not measuring accurately. And so their answer to almost every one of these questions is that's why we have people in the plant that go over and bang on it with a wrench to figure out which of the two isn't working. Almost everything you do has some immediate effect that you should see that what you did something. So very few things go to the blind because the reason you do them in the first place is to affect some specific change. Therefore, based on that, there's a way of already looking at that. What's more, shall we say, scary than that is I'm sitting on an HMI monitor that's here in Texas, and I'm sending you my slides in Illinois, and I'm assuming you're looking right now at a slide that says next steps, look at the attack, etc. But I have no method of feedback on that other than how you respond verbally over this channel. And so if we had somebody manning in the middle, they could be showing you different slides than I am. That rather than being a black letters on a white screen with a Kredsi logo, was red letters on a white screen with a UH logo. And I would have no idea that you weren't looking at what I was really sending. And so could you now deviate that a little bit? And that's where understanding what all the network traffic and what you're telling the device to do, what the device is hearing, what the device is responding back, making certain that all those lines are all actually correct and not being intercepted or changed in the middle, those are the key points. So in a way, you could argue it's an integrity of your overall control system that's operating the way you think it's operating and the way you're commanding it to operate. Does that make sense, Al?
Yeah, it makes sense. And I guess maybe what I would argue for is kind of orthogonal checks that this is taking place. So for example, you could have the feedback that you could get is not just us talking to you because we're pre-recorded and we're out having a long lunch, but if you have a TV camera in the back of this room, for example, then you could see through an entirely different signal chain the screen and says, yeah, that's what I expect it to be. And yeah, that could still be corrupted, but now you're requiring an adversary to do a lot more.
And to a degree, what you're describing right there is a good way of describing what we're trying to figure out how to make NSM, network security monitoring tools, do for us, is to provide that orthogonal check on what all the packets are actually saying, both ways, whether I'm actually using them and interpreting them or not. They paint the picture of what's actually on the wire as opposed to what's being painted on my screen.
Okay, are there any questions online? Thank the speaker. Is that it? We're done?
We're in, yeah, local spokes, we're in 301 next week.
All right, so we're back in the usual